Next talk is by Véronique Gayrard from CNRS and Aix-Marseille University, who's going to talk about aging in mean-field spin glasses.
I first would like to thank the organizers for this invitation. I will present a few results obtained in the past decade on the dynamics of the models that were introduced in the previous talks. So I will go fast over the notation and definition. I will denote by Vn, the n-dimensional discrete cube, and by sigma, a configuration of the cube. As we just saw, mean-field spin-glass Hamiltonians are centered Gaussian processes, Hn, indexed by this hypercube. And different covariant structures will define different models. In the P-spin SK model, the covariance of sigma and eta is a function, so n times the overlap of sigma and eta to the power p, where the overlap is a function of the Hamming distance that counts the number of spins of sigma and eta that disagree. And we see that as p increases, the off-diagonal elements of the covariance matrix decrease in modulus because the off-diagonal overlaps are smaller than 1 strictly. So if we formally let p go to infinity, what we get is the random energy model, namely a model whose covariance structure is now diagonal. And this is how Bernard Derrida introduced the random energy model in the 1980s. He proposed it as a simplification of the SK model. Of course, it is a drastic one. He later observed that an alternative way of simplifying the correlation structure of the SK model is to use an ultrametric distance instead of the Hamming distance, and increasing functions, say, instead of the p powers. And the family of models that he defined in this way is the generalized random energy model, which I will come back to a little later. Now, when studying the dynamics of such models, one thinks of the Hamiltonian as a random energy landscape in which a process evolves, crossing barriers under thermal activation. Then aging has been explained in this setting by the presence of arbitrarily high barriers at a given time scale, which trap the process and then slow it down. Now, different choices of time scales have led to different scenarios, so it is important to specify ours. In this talk, we will be looking at time scales that are exponential in n, with exponent of the form proportional to beta n. And on these time scales, we will study the model in the limit as n goes to infinity. So this is usually referred to as activated dynamics. And the dynamics we are interested in are Glauber dynamics on the microscopic configuration spaces. Namely, these are Markov jump processes, xn, that evolve on the hypercube with rates that are reversible with respect to Gibbs measure. Now, of course, there are several ways of defining a dynamics that obeys a detailed balance here. The most popular and the best studied so far is the random hopping dynamics that jumps from sigma to eta at a rate that is proportional to exponential beta n of sigma. This is whenever eta is a nearest neighbor of sigma on the cube. So we see that when it jumps, this dynamics chooses its next state uniformly from its n nearest neighbors. So it performs a simple random walk on the hypercube. And this is clearly not a very satisfactory feature. Physically realistic dynamics should favor jumps that decrease the energy. And the archetype of a dynamic that does this is Metropolis dynamics, whose jump rates are now functions of the difference in energy between the arrival point and the starting point. Here, these brackets are, with the little plus, denotes a positive part. So now, of course, the trajectories do depend on the random environment, on the disorder, and this makes the model a much harder object to work with than the simple random hopping dynamics, which explains why most of the focus first was on this simpler case. And later in the talk, we will see a third dynamics, a hierarchical random hopping, that somehow interpolates in difficulty between the previous two. And so now, since we want to study aging, as we all know, we have to introduce some time-time correlation function. These are functions of two times, tw and t, shown here on this picture. So time here is measured on scale Cn. At time 0, we start the process in the uniform distribution on the hypercube. This is to mimic a deep quench. And the time-time correlation function, Cn of tw and t, is then defined as the overlap of the state of the process xn at time tw, time being measured on scale Cn, and its state at time tw plus t, and I'll take the average over the law of the dynamics, so the average over the dynamical variables. Now, we usually say that aging occurs when, as n diverges, the correlation function, Cn, converges to a function that no longer is a two-point function, but depends only on the ratio of tw and t. And another scaling limit, we will see another scaling limit later in the talk. In this talk, we will only see those two possible limits. There are other ones that appeared in the literature, in the physics literature, that all have the same property that as n diverges, the correlation function is not time translation invariant. Now, of course, all our dynamics, Glauber dynamics, do converge to equilibrium on long enough time scale. So there is a time scale at which these correlation functions become time translation invariant and aging breaks down. And this tells us that the time scale at which we observe the process is really important in the observation of aging. So let me start now with the results. With the random hopping dynamics of the random energy model, so the simplest dynamics with the simplest model. And this is a picture of its dynamical phases as a function of the temperature. So beta is here on the horizontal axis, and on the time scale on the vertical axis, which is on a logarithmic scale. The time scale, Cn, is parameterized by a positive number, gamma. It is defined through this formula here. So it is equal to exponential n beta gamma to leading order, minus a logarithmic term that is subleading. So if we now fix here on the horizontal axis a value of beta, and if we move up along the vertical axis, we increase this time scale. Now, of course, the statics formally is here on the horizontal axis, and it is well known that there exists a static critical inverse temperature, beta star, such that for beta larger than beta star, Gibbs measure for the REM gets carried by an infinite countable sequence of configurations, the ground state configurations that will each carry a strictly positive mass in the limit, whereas for beta smaller than beta star, no single configuration will carry a positive mass in the limit. So this is the separation between high and low temperature. Now to this critical time scale, temperature here corresponds a critical time scale that is obtained for gamma equals beta star, and it defines the ergodic time scale of the model. Now, the ergodic time scale is the shortest time scale at which the process has time to find its ground state configurations. If we look at a slightly shorter time scale than ergodic, then the dynamics will never have time to find the ground state configurations. So you see that this ergodic plateau here is continued in the high temperature region by this diagonal. And what we have is that strictly above this diagonal, the process is in a stationary regime. It converges to stationarity as n diverges. And below this red phase transition line, in the entire region that is below it here, the process is aging. So more precisely, the limit as n goes to infinity of its time-time correlation function converges to a function of the ratio tw over tw plus t. And this function here is the probability distribution function of the arc-sine law of parameter gamma over beta. So you have its definition here, and you can check that this ratio, gamma over beta, in this whole region is strictly smaller than 1. Now, this result holds P almost surely in the random environment, in the disorder, so in the strongest possible sense. This phase transition line is also well understood. When gamma is equal to beta star, so here on the ergodic plateau, the process has a scaling limit. As I just said, the time rescale process, xn, on time scale Cn of beta star, converges as n diverges to an ergodic process, which is called a K process. I will not introduce these objects because it would take too much time, but the important point is that if we take a second limit and send time t to infinity, the K process converges to stationarity, and so from this ergodic low temperature transition line, we enter the stationary regime. Whereas if we, on the contrary, send time t to 0, the process enters the aging regime. And more precisely, if we first let n go to infinity, and then send the 2 times tw and t to 0, but keep their ratio fixed and equal to rho, then the correlation function converges to the same arc-sine law distribution function as before, with, of course, gamma equals beta star. What happens on the high temperature phase transition line is pretty different. Here, to obtain a non-trivial limit, we have to multiply the time correlation function by square root n prefactor, which in fact implies that along this high temperature line, the correlation functions decay to 0. So this summarizes more or less the results that were obtained in the past 15 years or so about the random hopping dynamics of the random energy model. And part of this picture has been extended more recently to Metropolis dynamics of the random energy model, where it could be proved that aging is indeed the same as in the random hopping dynamics. So the time-time correlation function converges to the same limit as before, with respect to the same convergence mode, namely almost surely in the disorder, and in the same domain of the gamma beta parameter plane, so in this region here, except that now the phase transition lines are not understood, so this is why I drew them in dotted lines. And in particular, we don't quite reach the ergodic time scale. Gamma here must remain smaller than beta star times 1 minus a term of order square root log n over n. So of course, this term is extremely small compared to 1. But once we plugged it into the definition of our time scale, it implies that we are off the ergodic time scale by this prefactor here. So there are at the moment technical obstructions to reach the phase transition lines. Now let us go back to the random hopping dynamics, but apply it to the Pace-Pinesky model. So here what we can prove is the following. So take any value of p larger than or equal to 3. To this p corresponds a value of gamma denoted by gamma c of p, such that below the red dotted line here, which is defined by the diagonal gamma equals beta up to gamma c of p, and then by this plateau here, then in the entire region below this dotted line, aging is in the Pace-Pinesky model is again the same as in the random energy model. This gamma C of P here, as P diverges to plus infinity, increases to the value beta star. And so this aging domain here increases to the full aging domain of the random energy model, which is here this dashed lines. And this result holds P almost surely if P is larger than or equal to 5, and in P probability if P equals 3 or 4. And unfortunately, we know nothing about the case P equals 2. That certainly falls into a different universality class. We also know that there exists a critical value of beta C of P, such that above the green dotted line here, which is diagonal up to beta C of P and then vertical, in this region here, the process is in a stationary regime. So, of course, we do expect that where I put quotation marks here in the low temperature region and long enough time scale above this plateau, we do expect that at some point this REM-like aging breaks down and gives rise to behavior that reflects the statics of the model, the structure of the replica symmetry breaking solution. But what can happen here in this region at the moment is just a completely open problem. We would need more, we would need to understand better the random energy landscape of the P-spin-SK model to go further in this direction. But this is why we will now turn to a simpler model, the GREM, for which the random energy landscape is indeed understood in detail. And I will look only at the simplest possible element of this family of model, which is the two-level GREM. As I mentioned earlier, the covariance structure of the Hamiltonian of the GREM now is a function of a function A of an ultrametric distance rho. This ultrametric distance is obtained by looking at the first coordinate where the two configurations, sigma and eta, disagree, and then taking 1 minus 1 over n times this quantity. Then the two-level GREM is defined by choosing the function A as a step function that is defined through two parameters, little a and little p. This function takes the value 0 up to p. It takes the value a from p to 1, and it's 1 at 1. So this defines the two-level GREM. In the k-level GREM, you would have a k-step function and so on. Now, the point behind this construction is that the resulting Hamiltonian is hierarchical. This means in our case that we can write the hypercube Vn as the product of two hypercubes, Vn1 and Vn2, so that calling sigma 1 and sigma 2 the configurations of this cube, the Hamiltonian Hn of sigma can be decomposed into a first-level Hamiltonian, Hn1 of sigma 1, and a second-level one, Hn2 of sigma 1 and sigma 2. And both these Hamiltonians are REM-like, namely these little Gaussians here, G's, are IID standard Gaussians. Now, here is what we need to know about the static of the model. We know that when A is larger than P, the extremes of the Hamiltonian are cascading. This means that to each first-level component, here labeled sigma 1 of an extreme of H, that corresponds several second-level components, sigma 2, sigma prime 2, and so on. Whereas if A is strictly smaller than P, then to each first-level component corresponds a single second-level component. Now, it is also known that the free energy in the cascading region, where A is larger than P, has two discontinuities at the critical values beta 1 and beta 2. And finally, we know that for beta larger than beta 2, Gibbs measure is fully supported on the configurations that carry the extremes of H, so fully supported on this cascade here. And And from now on, we will focus only on the cascading case, A larger than P, at the lowest possible temperature below beta 2. And the dynamics we will be looking at is the hierarchical random hopping dynamics. So this dynamics behaves like random hopping dynamics inside each of the two cubes, where it will choose one cube or the other according to the hierarchical structure of the Hamiltonian. So it flips a second level coordinate, a coordinate in the second level cube with at a rate that depends on the second level Hamiltonian only, and it flips a coordinate in the first level cube at a rate that depends on the full Hamiltonian H1 plus H2. And what we are interested in for this dynamics is to find out the phase separation line, the ergodic phase separation line, above which the process becomes stationary. And we want to work out the scaling limit of the process along this phase separation line to then deduce aging by taking a further small time limit, as we did in the random energy model. And so what we obtained in that is that this ergodic phase separation line, here in blue on the picture, is made of two parts. This first part here, this is a plateau of height gamma 2. And the second part, made of this curve here, that converges to gamma 1 plus gamma 2 as beta goes to infinity. And these gamma 1 and gamma 2s are numbers that are related to the extremes of the Hamiltonians, the first and second level Hamiltonian. Now, there exists these two curves here meet at precisely the critical temperature beta ft. This ft stands for fine-tuning. And what we obtain is that the time rescaled process along this curve has three different possible limits. Below this fine-tuning temperature between beta 2 and beta, at this fine-tuning temperature, and above this fine-tuning temperature. And each of these limits is a K process that take three different forms. Now, from these three possible limits, we obtain three different aging regimes by taking time to 0. So to state this result here, I will denote by alpha I, the ratio of beta I to beta, the critical temperatures to beta, with I equals 1 or 2. The correlation function is the same as before, the dynamical overlap between time tw and t. Here, the infinite volume limit has already been taken, and we'll take the two times tw and t to 0, keeping the ratio fixed equal to rho as before. And what we obtain is that below fine-tuning for beta smaller than beta ft, the correlation function converges to an arcsine law of parameter alpha 2. Above fine-tuning, it converges to p times an arcsine law of parameter alpha 1. And at fine-tuning, it converges to a linear combination of an arcsine law of parameter alpha 1 times alpha 2 and an arcsine law of parameter alpha 2. So what happens here is that, so suppose first that we are below fine-tuning, and place yourself at the critical ergodic transition, and then lower the temperature. What happens is that, so below fine-tuning, the second component of the process will go off ergodicity and enters the aging regime, while the first component will remain ergodic. And so what we see is aging on the second level. On the other side of beta ft, the converse happens. The first level component of the dynamics begins aging, while the second level component is still completely equilibrated. And at fine-tuning and at this temperature only, the two time scales on which the first and second level components become aging, then at this time scale they coincide, they are commensurable. And what we see is that the two levels of the process will begin aging simultaneously on the same time scale. So this picture is more richer, in fact, than the picture that was obtained, predicted by hierarchical trap models in the theoretical physics literature, where it has always been assumed that equilibration always comes from bottom to top, so bottom up in the tree. And in conclusion, this fine-tuning region here, we expect it to be extending to a much wider region, which is below this red dotted line here. But this is work in progress. So I will stop here.
Are there questions? Yes?
Are there any experiments that show that phenomenology?
I don't know. Perhaps somebody else in the room knows.
But there were numerical results, remember? You showed some, you mentioned some numerical
about
results.
Yes, the numerical results were done for Metropolis dynamics in the REM, in the random energy model.
I mean, that's not a real system.
No. So what was the question exactly? Numerical simulations for which model?
I mean, the colloid, the appertainers in 3 dimensions.
I do not know.
Well, I guess these results are rigorous within the scope of models. Are there other questions? If not, we'll thank the Véronique Gayrard and all the speakers all morning.